All right, welcome everybody, and thank you for coming on a Friday seminar for Stefano Alessandrini. Many of you are familiar with him, but he deserves a proper introduction. He's currently a Project Scientist 3 and Interim Deputy Director of WASAP, and many of us here have the pleasure of working with him. Yes, there we go. Sorry. Glad he's here to help.
But the most important thing is I remembered your gift because of that.
All right, so yeah, Stefano's been here for a while, since 2013, and does research in a wide variety of areas, particularly in wind and solar energy, probabilistic forecasting, air pollution modeling, turbulence mesoscale modeling, Lagrangian particle models, and I've even corrupted him to do some stuff in hurricanes, which has been a real pleasure working with him on that. Going back further in time, he got his master's degree in physics from the University of Milano, and later on got his Ph.D. in Piemonte Orientale, also in that area, I believe.
Yeah.
And then worked at this place called RSE. I'm not going to try to pronounce that, but for 12 years in Italy. And we are very lucky to have him here at NCAR in his variety of capacities. Also mentioned in his free time, he likes to be with family and travel, and he can still run a 3-hour marathon, so very impressive. So without further ado, I'll turn it over to Stefano.
Okay. Okay, my mic works. Okay, thank you, everybody. Can you hear me? Yes. I hope I won't. Thank you for being here after the lunch. I hope I won't mess with your digestion. And so today I'm gonna talk about my career from the beginning. So I like to start with just giving you just a brief overview. So as Chris mentioned, my first working experience was as an undergraduate student assistant at Enel, which was the national energy company for Italy. And then I was the work for my master degree thesis, and I started working on Lagrangian particle models. Then after a few years of the military service and some private industry experience in the private industry, I worked as a consultant at the Regional Meteorological Center in Pisa in Italy, doing operational forecasting. So I was advising grape wines producer about possible hail risk or freezing. So I have some credit for a good wines production during those years in the Tuscany. And then I went back to Milan at research on energy system, RSE. And I started working on, I kept working on Lagrangian particle models, but I also started working on renewable energy forecasting. And during that time, I took my Ph.D. At the University of Piemonte Orientale, and then the rest is the most recent story here at NCAR. So I just wanted to start my presentation with this exceptional winter storm event in 1985 in Italy, in Milan. I was first year in high school, and I remember because it is the highest ever recorded. It is an example of kind of bad decision making. This was created by a sudden polar stratospheric warming, and some Arctic air reached the mid-latitudes, and also there were humid air. There was humid air coming from the Atlantic Ocean, so it created this exceptional event. And so there were bad predictions, but that was kind of expected given the resolution at the time of ECMWF. It was 200 kilometers. And also meteorologists looked more like mushroom hunters at those times. It wasn't very, they didn't have a very good reputation because the skill, even one day ahead, was very poor compared to now. And as a matter of fact, there was a bad decision, all the snow removal vehicles were sent to Rome because Rome was also interested in exceptional snowfall, which is very rare at that latitude. And also was an example of bad design in terms of resilience to extreme, because as a matter of fact, the indoor sport arena, the roof of the indoor sport arena collapsed because the engineer didn't account for this possible event. Fortunately, it happened during the night and nobody died, but otherwise it could have been a massacre because it could several thousand people would attend a sport event, and still Milan doesn't have. Oh, that's bad. I speaking. I am done. I was complaining about Italy, so no, because as a matter of fact, so Milan doesn't have like an indoor sport arena yet, like for track at least, but that was a multi-sport. It was basketball, bikes, and track. And, but that's a different story. So let's start with talking about my first, so what I did basically during the early part of my career, it was about developing, improving Lagrangian particle dispersion models, which are tools to assess the impact of different kinds of emissions at the local scale. In particular, I use them for in the process of permitting power plants, because you have to, whenever you plan a new power plant or you do any modification to a power plant, you need to run these models to assess the impact of the emissions in the surrounding area. And these Lagrangian particle models are based in splitting the material, the pollutant, in many particles, which are assumed to follow in a passive way the atmosphere, the motion of the atmosphere. And so this is a Langevin equation which describes the turbulent velocity, and very simplifying. You can see like there is a component which basically contains the, it basically depends on the Lagrangian time scale, so the kind of memory of from the past of the past velocities. And this is the turbulent component, which is a stochastic component and depends on the probability density function of the turbulence. And very simple, so you can compute the concentration in a very simple way by dividing the domain into grid cells and into cubes, and you can count the number of particles in each cube, and dividing by the volume, you can compute the concentration at any time in the simulation. And so what I did was to introduce the simple chemical reaction to account for, to be able to compute the carbon dioxide, sorry, the nitrogen dioxide concentration, which is the substance which is regulated by EU legislation. So you can overcome 200 micrograms per cubic meter more than 18 hours in 1 year, for example. And so during night, you only have one reaction. So you usually release this nitrogen monoxide into an atmosphere filled with ozone, and you have a reaction which after a few kilometers basically creates mostly NO2 from NO. And this happens during the night. But so if you look at a profile, you see kind of, this is a plume section, you have a decrease in ozone, and most of the NO is transformed into NO2. But during the day, so there is an additional reaction, which is the photolysis that creates back NO and ozone from NO2. So you still have a similar kind of section, but with different ratio between NO and NO2. So how this algorithm works? In a very simple way, basically you have, at time t0, you have your concentration in any cell of the domain. You compute your concentration, you perform the Lagrangian displacement, you compute the new concentration C star, you stop the time and you perform chemical reaction, so you have a new concentration here, and you can redistribute, so you change the mass of each particle of particular reactant by looking at the ratio of the concentration after and before the chemical reactions. So this is an example in a real case. This is a power plant in Italy, in Chivasso, and there is this is the topography. So it's a power plant next to a hill near Torino. And so this is the transition between nighttime and daytime. So the photolysis here is practically absent, and here it starts kicking in with solar radiation increasing. And you see that the NO2 decrease suddenly, no, because you have the photolysis splitting the molecule and generating back ozone. And also the background concentration of ozone, there is a kind of hole here which shrinks when the photolysis starts kicking in. And so these are other things I've done on Lagrangian particle model, which is also improving the boundary conditions to deal with the convective boundary layer to avoid overestimating concentration near the ground, and also a plume rise scheme, which is still a hybrid Eulerian Lagrangian algorithm, and we tested it on the nice water tank experiment carried out by our colleague here, Jeff Weil, 2002, and basically you can see the interaction of this buoyant plume with the stable, so you have the temperature profile here. You see like there is a convective layer here and a stable profile after. And you see the interaction of the plume with this stable layer, which slow down the vertical motion. But you still have some material going beyond this inversion layer at the top of the boundary layer. And this amount of material, so having this amount of material right, it's particularly important in applications like wildfires, plume from wildfires, because that material is the one that is transported at very high, far away. No? And usually, this is very simplified in most of the models. So these kind of plume rise schemes are very simple, the one that are used nowadays. So we plan to implement these schemes and we hope we will get funded. We have included it in a proposal that Tim Giuliano is leading now. So this is the first application I did with the Lagrangian particle model when I came here. So I don't know how many of you are aware of this, but Japan basically dedicated an entire sector of industry to build balloons to attack the US during World War II. And they planned and they tried to drop many bombs to trigger wildfires and also create basically panic in the population. No? So there was a similar fear in recent years that the same technique would be used by a hostile country from Asia. And so we did this study. I cannot say too much, but so what we did was run WRF for an entire year over this domain and running this Lagrangian particle model, simulating the release of these balloons in the upper troposphere, and looking at statistics like what is the minimum traveling time to get to the US. And you can see that for Alaska is even less than 1 day, and this is in January. And in Oregon is probably less than, a little bit more than 2 days. And of course, the most favorable conditions were in the winter, where the polar jet stream is at lower latitudes, while in the summer it's very likely that these kind of balloons wouldn't get here. So this is the first application, and I have to give credit to Francois Wardenberg and Ron Schuh, who helped me with this work. So this brings me to another application of Lagrangian particle model for national security. It was for the planning of Jackrabbit 2 experiments. So this is an experiment which took place in 2016 and a Dugway Proving Ground in Utah, and they released chlorine from a tank. and then try to study the dispersion of this plume of chlorine. And you can see that they did that also trying to simulate the urban environment, putting these containers around the release. So we use the global climatological analysis tool, which has been traditionally developed at NCAP, now the National Security Application Program, here at RAL. This tool can perform different kind of jobs. One is the climatological reanalysis, a target reconstruction, or the seasonal forecast. But all these jobs involve running WRF and ski path, which is a Lagrangian path model, and over a target period, which can be, we can run in retrospectively or in a kind of seasonal forecast mode, which is basically having the NOAA CFS forecast driving the WRF ski path simulation. After that, you do like a clustering analysis with the self-organizing map, and you come up with typical days with kind of likelihood. So we help them in planning the most likely scenario in terms of plume dispersion in order to be able to planning the sensor locations around the release. So what we did was running the seasonal forecasting mode, which is based in having the NOAA CFS forecast initialized 1 month ahead of time. We used a time-lagged ensemble. We target the period of September 2016. For those, so we used this dynamical downscaling, which involved in running WRF and ski path, and then we ended up with 480 days, which were processed by the self-organizing map, and we came up with 6 typical days. So 6 likely scenario of plume dispersion. And as a matter of fact, so here you see the climatological reanalysis, so what you can have as a first typical day on the left, just looking at climatology. In the middle, you have the one that we came up with this seasonal forecasting approach. And on the right, you have after the fact, the reconstruction. So you see how we did much better than climatology in kind of predicting what would have been the most likely plume dispersion, no? For this kind of experiments. Okay, so now I transition a little bit speaking about post-processing, which is the other kind of topic that I have been involved both before coming here and after. So model post-process, so as you might know, all the model simulation have some uncertainty, and they don't reproduce reality. So because of the resolution, because of physical processes that are not resolved or are not correctly reproduced in the model. And so the idea, of course, the simple solution is to try to improve the forecasts by basically build a statistical relationship that links the forecast to the reality, which comes from observations. I mean, the pioneer work in this field is from Glenn and Lohr in 1972. They were the first who introduced this approach, which they call model output statistics. And it is used nowadays as well. So why ensembles in general and post-processing can be important for renewable energy? So an example is the day-ahead market. The day-ahead market, all the producers of renewable energy, they have to, in many countries, they have to basically sell the energy 1 day before. So they have to promise each hour of the day, of the next day, how much energy they are going to produce with a wind farm, for example. So, and you pay penalties if you don't get these forecasts right. And the penalties are based on different price of energy compared to the price that you will get if you get the forecast right. And just to very quickly summarize this slide, so first of all, you have to get the forecast right. So post-processing helps because it improves accuracy and reduces the penalty. But also, there is a value in the ensemble because it has been demonstrated that if you solve this this equation coming from this economic model, you optimize the revenue. But this equation involves this probability. And so basically you have to solve the equation and find EC, which is the probability of the energy being lower than EC. And this probability can come from the cumulative density function, which can come from an ensemble. So the ensemble gives you the right input to optimize the revenue if you if you are a wind farm owner. And so how usually I approached, and many approach this problem before before I saw the light in form of Luca Delle Monache, who introduced me to the analog ensemble. But before that, I basically, and most of the community was running an ensemble like ECMWF or Cosmo Labs, then doing some post-processing with neural networks or model output statistics based on linear regression, and then you apply the power curve to have the ensemble power forecast up to generally 72 hours ahead. Okay, but so as you can see, you have to do kind of two steps, like a first correction and then a second correction with the power curve, which can be theoretical or empirical. Empirical, it means that you build it by looking at the local wind observation and power measurements, or you can have it theoretical, which means that it comes from the factory. No? So to make this process more simple, so when I met Luca, we discussed and we start working on applying the analog ensemble for renewable energy. So this is a kind of, I'll go through this technique very, very quickly. So how it works, let's say that you have a forecast up to 24 hours of wind. So this is your target forecast at 12, which is your target lead time. You look at an archive of past forecast. You find the forecasts which are more similar to the target forecast. And then you can take, so in this example, I just picked two forecasts. And then I take the corresponding wind observations. But instead of wind observation, you can take directly power observations. So you don't need the second step so you don't need the power curve anymore. And you can go directly to power from wind predictions. So that makes the process very simpler and even more effective most of the time. So you can have this ensemble, and you can build your new forecast, which is basically made of past observations. You can take the ensemble mean to have a deterministic forecast, or you can leverage the whole ensemble members to have some statistics or probabilities of some kind of production. So how we applied it, so we tested on a real case. So we used the economic rules that were in place in Italy during that year, and we compare like the revenue of this real wind farm made of 9 turbines. And we demonstrated that using the analog ensemble, so using the economic model and using the PDF coming out of the analog was rewarding the producer more than having a deterministic forecast made with a simple system using RAMs and then a neural network as a model output statistics, or even of course, better than climatology, which means just giving a constant prediction with the mean wind. But still, you pay some penalties because the forecasts are not, even the probabilistic forecast, they provide uncertainty, but they can fail, of course, but still you increase the revenue, you know, compared to other techniques. Okay, so these are some of the applications and papers. So this technique has been applied to a variety of applications, going from wind speed to wind power, solar, load, air quality, tropical cyclones, and also downscaling. So the feature is that there is no need for initial condition and model perturbation strategies to generate an ensemble, and so you can use a higher resolution model for an ensemble prediction. So because you only need one real-time forecast from a deterministic model. It's very cheap in real time compared to standard methodological ensemble, and it has proved to be bias-free reliable, to generate bias-free reliable predictions. And the most important thing is that for renewable energy, you don't need power conversion. So this is an example. This is work for the Kuwait project, which was led by SUOPT, and Pedro Jimenez developed WRF solar targeting this application in particular. And so here you see basically the bias from two versions of the analog ensemble. You can see compared to WRF solar, which tends to overestimate the solar radiation, basically because of the shallow cumulus representation, bad representation in the model. You can see like a reduction in bias and improvement in terms of root mean square error. This is another application of grid prediction. So we used, this is still point-based, but we used the National Solar Radiation Database, which was developed by NREL. This is a work sponsored by DOE NREL. Worked together with also Jimmy Dudia, and also Jouet and Pedro helped a lot. Actually, Jouet generated these plots, and you can see that. So here you see the WRF solar EPS, which is an ensemble generated with the stochastic physics perturbations. You can see how can reduce the root mean square error. So you can see WRF solar NEN, but you can see that indeed the best performance are achieved if you apply the analog ensemble after WRF solar EPS. So this is a combination of the kind of most traditional dynamical ensemble and the analog ensemble. And in this case, the advantage from the analog ensemble is that is able to use as one of the predictors the spread, so some information about the probability of the distribution. This is another application for downscaling. We built the Italian wind atlas using the analog ensemble for downscaling wind, and this is a qualitative comparison between dynamically downscaled WRF wind field speed and the analog ensemble, which is a statistical downscaled wind field. So we also improved the algorithm to take into account for rare events. So once we apply this the technique to over this domain to have like a gridded wind speed prediction, we noticed that it wasn't able to predict correctly some extreme events, or not really extreme, but just high wind speed events which were relatively rare in the data set. So what we did, you see here, there is like wind speed is much lower than the analysis here. And so we applied this technique which tried to adjust when you have a forecast which is kind of doesn't have similar forecast, and it's a kind of outlier, no? So here you have a forecast and wind speed. What you do is you kind of compute the difference between the current forecast and the past mean forecast, and you apply this difference to the past observation here, and you shift them forward to better represent the possible outcome in these kind of rare events. So we applied this technique, and we compared with the standard ensemble here. This is the analysis. This is an example of forecast of some ECMWF EPS, bias corrected and calibrated with this analog ensemble coming out from high resolution IFS forecast from ECMWF, and we were able to kind of correct this lack of high intensity wind speeds. So this is another application about tropical cyclones. This is work done with Chris Rodzoff. Chris led this work, and we demonstrated that we were able to improve, so that you should look at the green line, which is the analog ensemble based also on the IVCN, which is a consensus model. We were able to improve upon H-WRF, which is in blue, in a statistical significant way. And also we compare it with the other traditional technique like quantile mapping. But yeah, and then this is an example on the left here of the possible, one kind of forecast you can get out of this technique. And you can see the confidence interval of the intensity and how in this particular example, the ensemble mean is closer to the real intensity compared to the H-WRF simulation. So we applied it also for rapid intensification and track. And finally, this is one of the recent applications for fog hazard in BR. This is a work that is been led by Rajesh, but Will did most of the work in babysitting Abhishek, and it was very early morning meetings. So yeah, Bihar is a state in India which accounts for about 50% of total road accidents, so it's a very serious problem there. So this is the number of fog events in the most recent years. You can see there, and of course the season which is most affected is the winter from November to February. And this is, so what we did is, so fortunately they have a huge network of observations, very, very dense network in which they measure temperature, humidity, and wind speed, and other variables. So we were able to have kind of gridded prediction based on observation. So we're still point-based, but very dense. And so we ran WRF, and then we apply the analog ensemble. Here is for example, this is the probability of detection of WRF alone and WRF with the correction of the analog ensemble. So you see a big increase. Also, the critical success index improves a lot. And this is a very recent that Abhishek sent us a few days ago. You can see like the forecast issued the day before and the actual fog observed by the satellite during so basically confirming the prediction. So, okay, so let's go to more the final discussion. So challenges for the near future. So this is, I have to give credit to Tom Hamill. He was presenting this slide last year at MS. So there is this new trail of deep learning that is probably destroying traditional technique, a simple technique like MOS or analog, no? And so how kind of approach this problem is to, first of all, try to leverage skills and try to compare these old techniques to the new one, with the new ones. So what we did, for example, is so we leveraged the visit of this PhD student, Will Chapman, which now is a colleague. He works here, but at the time was a PhD student from Scripps, and we analyzed this flood event in Italy, which occurred in 1994. So the idea was to see if with the current technologies we were able to improve predictions compared to what happened like 30 years ago, okay, 1994. So we ran WRF. And fortunately now this region has like a gridded data set of precipitation made of objective analysis. So they merged the radar observations with point-based observation of rain. So it's possible to have a 30 years long gridded data set of precipitation of the region. And we compare the WRF with this gridded data set of observations. At the center, you see just simple bias of WRF after the INEN, so the analog ensemble. And on the right, we have the convolutional neural network application. And so the difference is the analog ensemble is point-based, while the convolutional neural network, you provide the entire field in input. So it should be able to catch some error characteristics that are dependent on the shape of the field rather than the simple point value. So this is an example, and this is a more clear picture of what happens. So you have, on the left, you have WRF plus INEN at the center, and then convolutional network. Sorry, there is a mistake. It's WRF plus convolutional network. So the analog ensemble is not working on the right picture here. And so you can see that in terms of statistics, the convolutional network indeed does a better job in decreasing the root mean square error and the bias compared to the analog ensemble. If you look at the extreme value over this grid during this event, probably the analog ensemble still does a better job in getting right the largest observation of rainfall. Okay, so the take-home message is that you can still have some value in these simpler methods that involve maybe less resources to be run. So finally, so this is another example. So a very simple machine learning technique, which is KNEN. This is a work I just presented at AMS. KNN compared to users, which is K nearest neighbor. It's a very simple technique. And I applied it for source time estimation, so to determine the strength and the location of a point source just by looking at the downwind concentrations measured from sensors. So what you do is to basically find the nearest neighbors, comparing each array in a verification data set with the arrays in the training. So you create a very large synthetic training by running a model a number of times by changing the location. And so you simulate possible concentrations, and then everything disappears. And then you find the nearest neighbor in your synthetic data set, which provide you with the labels. So you find the nearest neighbors and the corresponding labels, which in this particular case are the X and Y, the coordinates of the source location. They tell you the prediction. No? And I compare this with a traditional source time estimation approach, which involves running, so you reverse the wind and you run the plume model backward, and you look at the overlapping areas. The maximum overlap gives you the source location. Okay. So I compare these techniques, so KNN traditional source term estimation approach and also neural networks. And I applied it to this FFT07 experiment. And I found out that, for example, in this particular application, KNN and the backward approach in green are very close to each other, and they have similar accuracy in a real case. But in the synthetic data set, I found that indeed KNN can provide better performance. So this is the mean distance error compared as a function of the number of receptors in each line of receptors downwind. I found out that KNN can provide indeed the best outcome. So the take-home message is that a very simple machine learning technique, which is KNN, compared to neural network, can indeed can still be competitive in some applications. So yeah, that's just a question, no? Like, so in the end, is the deep machine learning train of thought a challenge or an opportunity? So I think it is, of course, it is both, because so we should actively contribute to the development of this new model, but that's a challenge because many of us maybe have a gap in the education because we have not been trained in data, no? Machine learning and data science. But we can still leverage them to enhance our application and drive innovation. For example, Jared has now been awarded with an internal award regarding the inclusion of this data-driven model issued regularly in operation by ECMWF to see if we can still improve so how they perform in the US, specifically targeting renewable energies. And so we plan to see if there is an added value in also including as a potential additional model in our multi-model statistical post-processing, like such as diecast, for example. And also we should engage our established sponsors as much as possible to indeed, I think, address the potential educational gaps, and also leverage the young scientists which have maybe more energy than to take over and try to explore this emerging landscape. So with that, I want to thank people that have been important for me, in alphabetic order, not in order of importance. And then, yeah, also I wanted to present this slide about imposter syndrome, like how to, because I think many of us are kind of affected, especially, I mean, I feel sometimes like an imposter with all the things we are exposed at RAL. We have to try to be experts on many topics. So I think the right way to approach is to think that what you know can still overlap with somebody else's know, and not feel like isolated as. So that's just suggestion, because I know that, like, statistics say that 80–90% of scientists feel like imposters. So I know that all of you at some point in your life felt this way. So with that, I just take questions. Thanks.
Thank you. We have a lot of time for questions, and we also have people online, so feel free to type that in the Slido. But first, let's make sure everyone's reviewed the workman's comp before I try to throw this. This first time, I'll try.
There we go. Great talk, Stefano. With my question specific to the KNN approach, did you look at any cases where you had a kind of mixed source region? So you had influence from multiple different trajectories, or what do you think would be the performance in that case?
Yeah, it's a good question. I haven't tried that. Indeed, that can be indeed a problem, but that would be challenging even for traditional methods. backward plumes, because I think it can make the degrees of complexity, degrees of freedom. So if you have any, so as far as I am concerned, I always try to approach this source time estimation with a single source. But for local kind of domain relatively small, and things can become much more complicated, then probably this approach is not appropriate for a larger domain where you have multiple sources, of course. Yeah.
Anyone else?
All right. Thanks. This is a really fun talk to watch, Stefano. On one of your last points was your deep learning as a new opportunity and challenge, and the need to engage earlier career people here. And I feel like the real trick is engaging earlier career people who are already in that area and have a better understanding of it with people who have more experience and have run into all of the problems that they're going to run into already in other methods, because there's still a lot of the same lessons that have to be learned. And I see this in early career scientists where they're amazing at running some of these processes, but they skip this like order zero problem over here that people who've been in the field for a while could have told them about ahead of time. So how do you best get everybody working together so you leverage all of those strengths?
No, I completely agree. Yeah, of course. But that's the nature of our work, no? Yeah, at RAL. No, we work on projects, and you always have a mixed level of experience. So it's crucial indeed, because I see many times, as you said, so they are super expert in these new techniques, but they miss the overall picture, and they don't see, like, maybe they're missing something, like even simply preparing the input data set, they're missing something that for us can be straightforward. It happens all the times, and I mean, I've experienced that already. Many projects regarding especially air quality, we work with data scientists, and we see that sometimes they really need our help to put, even, as I said, to prepare the data set in the right way, like, for example, simple things.
That's an easy handoff. Good. Thank you, Stefano. That was a really nice talk. I have a question. So we have a customer ongoing for years who relied on, the GCAT reanalysis technique to determine typical conditions in a certain part of the world they were interested in. And now we have the capacity to do the CFS and downscale that and look a month ahead. Is there more weight being placed on one or the other? Because they yield different results, especially with climate change. How are we handling that, and what do you see as, the progression as we work with sponsors?
So in terms of I think the sponsor you're thinking at, I think that we see more interest in trying to move away from climatological reanalysis and rather targeting this seasonal forecast technique, which has been developed in the last year from our group, no? And what we do is thanks to work with Scott Mitch and Yong Shin, we are trying to indeed assess the performance compared to climatology. So how far ahead it's worth to use this product. And for now, we have seen that there is some value if you go 1 month ahead. But if you start going like 2 or 3 months ahead, you end up having the same kind of answers as you would get with the climatological reanalysis in terms of typical days. So that's what our advice for now to the sponsor is, that, like, if you target 1 month ahead, you can there is value in this product. But so we are ready to implement other global models in this product. That's the important thing. As this model improve, we can definitely go away from NOAA CFS and use other models, with other sponsors like ECMWF model, for example. Or now UFS from NOAA should be operational soon, I think, if it's not already. So we could switch to those models indeed, and because a CFS it's pretty old model. So
Thank you.
yeah.
Some specifics of analog ensemble, which was developed as a point-based method, but you've been very creative in applying it as a gridded method. But one of the issues with that is often, as you're doing it point by point, you can end up with disparate neighboring values that come out. And again, you've been very creative in applying things like Shocky Shuffle and that, but there's still limitations here. And I'd love to hear you discuss how you think, to what extent is the analog ensemble, as you have applied it in some of your most recent cases, really a 2D method versus still a 1D method that you're smoothing?
Yeah. So I think that a crucial step is the ground truth. Now, if you have how you create your ground truth. If you have a gridded data set which is reliable, then the point-based approach is still competitive, I think. But if you don't have a reliable analysis or ground truth, gridded ground truth, then maybe you run into troubles. But so we have applied. So we have collaborators. There is like Jan Keller visited us from Germany, and he generated a reanalysis data set of precipitation. Using the analog ensemble, he was able to expand the kind of area, search area around the point. So there are ways to make it more 2D based and retaining some information about the shape of the meteorological fields rather than just point values of that. So I don't know if I answered your question.
I think
Yeah, but for example, the application I show about the solar irradiance was based on using this gridded satellite. So this gridded satellite derived satellite data set, which for solar irradiance is very convenient because so there are now techniques to have these high resolution gridded products. So these allow like a point-based application to be still effective, I think. But in terms of discontinuity of the field, as long as you use the ensemble mean, you don't run into troubles, I think. Like there is no discontinuity. But that, again, depends on the underlying gridded data set that you have.
Thanks for the presentation, Stefano. My question is about the machine learning and especially for extreme events. In particular, creating synthetic data for those events. You addressed one part that was kind of linearly addressing that. What are your thoughts on really implementing nonlinearity in these data sets?
So my thought is that so there are techniques out there to make these. So I have attended many presentations in which they target the use of this machine learning technique for extreme events. So what I can say is that you have to make them more frequent in your data set, basically. You have to, or the other technique is to try to weight more the errors coming from these extreme events. So you have to penalize the error more for these single events in order to balance your training, your machine learning, to try to cope more with these extremes. So there are techniques, of course, but out there, and people are tackling this problem.
So do you think like it would be advantageous for us as institution to invest on creating such data set?
Yeah, but that really yeah, of course. Yeah, I can say generically yes, but it depends on the particular applications, and I mean it's a very generic, I think, problem, no? Like, of course, yeah.
Yeah, thanks, Stefano. Great talk. So analog ensemble, it's a magical technique, means every area that we try to apply it to, it always works. I'm wondering what are your thoughts on applying this to space weather, which can potentially lead to collaborations between RAL and HAO?
Yeah, thanks for this question. So as you are aware that we wrote this proposal with collaborating with HIO to try to apply post-processing to predict some space weather-related variables, and I'm not sure if it will be funded, but in any case, from my first thoughts are that that's a very early. So they are in a really early stage. The kind of research is in a very early stage. The forecasts have a very low skill for now. They don't even perform analysis very well. So I think that there is potential, but probably there should be an underlying skill provided by the numerical model before the analog can provide some added value. Because the analog still need to have some correlation between the prediction and the observation. And so if that is missing, it's not magic at all. Like you have garbage in and garbage out, basically.
Thank you. No, I was actually inspired by what we saw during fog, right? We have very, very low correlations. But I think we can talk more.
Yeah. But it was still,
Okay, I think we have time for one more question. Very good discussion here, so very appreciate that. I did have one question. I know we've talked about this a little bit, but with all your experience in plumes in the past and our work recently with air quality, what do you think like UFS and other models that are used for air quality now can do to improve their fire emission plumes?
So there are many source of uncertainties as far as, so I'm not an expert, so I can talk about a little bit plume rise now, but so my understanding is that there are also other uncertainties regarding the emission factor, depending on the kind of area that is burning, like a suburban area, they provide different emissions, of course. Now there is a lot of uncertainty in the emissions. That leads to uncertainty in the plume rise, no? And so, as you know, most of the model, they just compute they have this parameterization to compute the plume height, and they linearly distribute the material from the bottom, from the ground to the plume height, which is not realistic in most of the cases. No, you have most of the material sometimes goes beyond the boundary layer into the upper troposphere, and it's transported far away. It's I think to answer the question, I think the most source of uncertainty is in emissions. Also how to predict emissions, because they don't. So when you generate a forecast 3 days ahead, you don't know how the emissions will be in 2 days, they will be. So that's that creates uncertainty in the plume rise and the wind that will affect the plume, and so yeah.
All right. Well, thank you for this excellent talk. Let's all thank our speaker once more. And you know where to find